uh, the my goal in this video is to not come out as a teacher. Hello. Today what we are going to do is we have to discuss Schrödinger equation for a free particle. Before finding it for free particle, I thought we should discuss how do we define a potential, because for a free particle we know that potential has to be zero. Um, but how do we generally define potential in quantum mechanics? I'm not going into the function form because that is very complicated and not complicated, but there is no point of discussing because it's a function of x. It happens, the potential can be. So when we define a potential, let's discuss it here. Let's say it's your axis that defines potential. This is the axis that is defined x-axis. This is a point 0. Let's say this is your potential V. And now the potential can take a lot of forms here. Now we can make the potential like this. We can define the potential as now this is a potential. If you can see, if we point out this point as, let's say, V2, and this point we have to V1. Now you can see in this potential V of x tends to V2 at x tends to plus infinite. Is that when x goes to plus a positive side infinite, the potential Vx will have a value called V2. V of x is close to V1 when x is equal to minus infinity. You understand this? Now when this is happening, so you have to define a point here. If this is the plot of potential, this is the point of minimum. This is your V minimum. This is a local minimum that we have here. Now look at this. These are the potentials only. But when a particle moves inside a potential, the particle has some kind of energy. So when we define that energy is defined as this. This is E. Now here, look at this. Look at this point. This is the energy of a particle that is crossing the potential at 2 points. This 2 point, let's say this is x1, let this point is x2. So now you can understand that this is a potential that is going down. Energy of the particle is always less than V1, but at this point, from this point to this point, which we call classical limits, or we call these 2 points are classical turning points. Between the classical turning points, we have the potential less than the energy. Okay, now look at this. This entire plot can be divided into 2 parts. One is this part, one is this part. Okay, now these 2 parts are called 2 different names. This is called continuum state, and this is called your bound state. this state, when a particle is in this state, then we call it a bound state. Basically, a bound state is defined when V minimum less than E means the energy of the particle, and V1. Now, another thing we find out across the line when we study quantum mechanics more deeply, then we understand that the bound states are the only states that gives us discrete value. Discrete value, we always know what is a discrete value, what is a continuous value. I mean, the study of quantum mechanics starts from understanding that energy are discrete. And we also in quantum mechanics we found out that this bound state is a system that gives us energy spectra when it is discrete energy spectra. Now, in this kind of system, what is very easy for us is to understand that what are we dealing here? What is a bound state? So we have to define that a bound state is a state in between the particle cannot reach the infinite phase. It is trapped in between two classically turning points, and in that classically turning point, it is giving a value of energy to be discrete. That's a bound state. That's how we'll define a bound state. Now, in this bound state, there is also another study that happens that we know in quantum mechanics we define energy as n, which means energy is dependent on the value of n. Those who know quantum mechanics, they know there are very famous two states. One is a harmonic oscillator state, defined as this. Other one is in the last video I discussed, which is one-dimensional potential well. Now, in those two states, there are two differences. I mean, there are a lot of differences. The potential here is different than the potential here. But the basic few differences are, when we both are bound states, we know. When we define this n, we take n equal to 0 to 0, 1, 2, 3. But when we define this n, we define 1, 2, 3. We don't include 0. Now, one more thing which is very important when we are studying bound state is that in a bound state, we always need to find, I mean, it is easier for us to know how to find the number of nodes, because it is always bit tricky to remember the plots of each bound state. So better to remember what is the number of nodes. Now, if you don't know what is nodes means a point where the wave function goes to 0. It means that this is let's say I'm doing for one-dimensional potential well. Now, for this is our limit. So what will be the value of psi? For n equal to 1, we'll have ground state. Now, in this system, this is your ground state. Yes or no? Yes. Now, this starts from here, ends here. In between, there is no point where psi x goes to 0. So this waveform, which is your psi 1x, this has number of nodes as 0. When you draw the second state is of some nature like this. Here you have one node. So n equal to 2 will have number of nodes 1. Now how do we remember this in a very short form? How do we remember this in a very short form? Because that's what matters. That's what matters in this kind of discussions, is that what is the shortest form to remember this kind of things. Remember, whenever ground state starts from n equal to 0, if ground state starts from n equal to 0, that means n equal to number of nodes. But if ground state starts from n equal to 1, that means n minus 1 equal to your number of nodes. Now this is the one dimensional potential well. Here what is our system? Our system starts from, the ground state starts from n equal to 1. So you can see in this system the number of node is always n minus 1. Here it was the first state where n equal to 1. What is the number of nodes? 1 minus 0, 1 minus 1 equal to 0, or n minus 1 equal to 0, which is basically no nodes. In the second state, n equal to 2, 2 minus 1, 1, only one node. But in case of harmonic oscillator, this is for harmonic oscillator, quantum harmonic oscillator, and this is for 1D potential well. We are not discussing that. I am only focused on this part. I mean, in this video, I am not focusing on that. I am only focusing on this part. I wanted you to know what is a bound state. Now, we also found out one more thing. We also found one more thing, is that in a bound state, when we are taking one-dimensional potentials, first of all, it has to be discrete. Second of all, it has to be non-degenerate in nature. Now, what is a non-degenerate? There is something called degeneracy. What is a degeneracy? Degeneracy means having same value. Or if I tell you there is a eigenstate. Okay. If that eigenstate gives you a value of so there is an operator, there is an eigenstate. When we operate that operator on an eigenstate, you will find an eigenvalue and the eigenstate. Now, if there are different eigenstates, but they are giving the same eigenvalue, if there are different eigenstates and giving the same eigenvalue, then all the eigenstates will be considered as your degenerate eigenstates, and the eigenvalues will be considered your degenerate eigenvalues. This is a different thing altogether. But in a case of bound state, in one-dimensional potentials, we also figured out that it has to be discrete in nature and non-degenerate in nature. It shouldn't repeat the value. It should not repeat the value. It means here we put n equal to 1, you will find h bar square pi square by 2m square. This value will not be repeated in entirety of it. This can be repeated in 2-dimensional. This can be repeated in 3-dimensional, but not in 1-dimensional. And okay, now let's discuss something very fundamental, which is a free particle. I have to wipe it out, and I think I will edit it out. Now, what we're discussing in this subject was our free particle, or a free particle. Now, first of all, it is not a bound state system, is it? Is it a bound state system? No. So we cannot say it will be discrete or not. We cannot really say that this will be a discrete value or not. This is the first thing. Second thing is that We solve it exactly like we solve that question. This is our Schrödinger equation. Everybody who studies physics, they know this equation. Even +2 students know this equation. It is an atomic structure. I mean, it was an atomic structure when I was studying in 2016 to 17, first year, +2. This was an atomic structure. Now, if the free particle means V equal to 0, it means the potential is 0. That means that the system exactly turned into what we have done in the last video. Now what we'll do, in the last video we defined a K. K is your root over of 2 me by h bar square. Now this system becomes okay. Now everybody, I hope everybody knows how to solve a differential equation. If you don't, you should learn, because you are studying physics. You should know how to solve a differential equation, because, and it is very easy. You know, it's very easy. So you should study if you haven't, and I hope you have. Now solving it, what happens? We take this as d square, and this is our k square. We equate it as 0. Now that what happens? D is equal to plus minus ik. Yes. Now the solution of psi will be first function will be a plus, let's say, e to the power minus I k x, plus another function would be this let's say is plus. First, then the second will be use minus I k x. Okay, understood? Now look at this. This is a very classic formula. We solved this question in sine and cosine in the last video. I used this as a system, because I'll tell you when I calculate the probability density of it. Now look, this is a function, but it is only dependent on x. We know the wave function can be dependent on x. It can also dependent on time. Yes or no? Yes. In quantum mechanics, when we define psi of x t, what we do, those who don't know this must remember, because it is very important postulate. I e t by h bar. It means if you are given a wave function at time equal to 0, then you can transform it to get at time equal to t. This is the formula. This is energy, this is time, and this is your h bar. H bar, I hope you know what is h bar. In a class, when I teach students, I ask them, go to them and ask them, okay, what do you mean by this? What do you mean by that? I ask every question, but in the video, I cannot do that. The limitation of this medium is what makes this medium a very hassle-free medium. And one of the drawbacks are that whoever is communicating, he or she doesn't know really who is he talking to or who is she talking to. It's fun. I'm making my second video. I'm happy, Okay, now look at this. This is defined as this. We already know there is a formula E equal to h bar omega. So if I have to define E by h bar, we can define it as omega. Instead of E by h bar, I can write it as omega. Now look at this. When I put omega here, the exponential part is going to transform. So now psi of xt is equal to, this is the first term, which will be I into kx minus omega t plus a minus e to the power minus I kx plus omega t. Got it? I hope you got it here. I hope you got it here. Now look, the fun part will begin here, because everybody would be thinking, this is a very easy solution. Why people say this is very complicated? Why people say there is no boundary? There is somewhere there is a boundary, somewhere there is no boundary. What's the problem? The problem will come here. What happens when we try to calculate the probability density? Probability density of the system can be calculated by, this is basically means that you take psi star, that is the complex conjugate of psi, and multiply it with psi. This is your psi, you have to take complex conjugate of it, and then you have to multiply it. Now there is a thing here which you need to understand, that this is one wave function, this is another wave function. This is one wave function, this is another wave function. How did I know how did I know this? Because I studied it. Look, how do we define it? Look, everybody knows in quantum mechanics there is something called an operator of momentum. It is defined as minus I h bar del by del x. Okay, now when you operate minus I h bar del by del x on this function, on, let's say this is called our psi plus, this is called psi minus. You will know now why I use it plus and minus here. You will know now. Look, if you put this operator on this function, what will you give? What will it give? It will give us ik, and the function is, let's say, psi plus. Okay, I should have written it this way. We put momentum operator on psi plus, means this function, and it gives us this value. What is the momentum value of this momentum? I minus 1 minus plus, which is h bar k psi plus. Now look, this function is psi plus, this function is psi plus. This is the operator. So now what is this? This is the eigenvalue of momentum operator. On psi plus. This part. What value it gives? It gives h bar k. What? H bar k. Now the same thing if we do on psi minus, we will get minus h bar k, psi minus. Now look at the eigenvalue these two functions are giving, psi plus and psi minus. What are the momentum eigenvalue of these two wave function? One is a plus h bar k, one is a minus h bar k. Basically it means that one is propagating towards positive, one is propagating towards negative. It means this wave is going along this direction, this wave is going along this direction. So when you calculate the probability density, you have calculated the probability density of two different waves. So now come to probability density. Probability density can be found, let's say this is psi plus, psi minus. If it is psi plus, then the wave function will be a plus, and if it is psi minus, it will be a minus, and both square. This is your probability density. Yes, very easy to figure out. Okay. Now, one thing that you have to think about here in this system and in this kind of questions is that what does this system already tells you? What does this kind of system tells you right now? Right now, it tells you one thing first. First thing is the probability density is coming out to be a value or a constant value. Probability density is coming out to be a constant value. And one more thing it says that it doesn't depend on x or t. Probability density does not depend on x and t. Now, after studying this part, let me tell you something else. Now, when we calculate the velocity of a wave, we can use this formula omega by k. Everyone knows we do that. Now, omega by k can be considered as E by h bar k. H bar k. Yes or no? Because E equal to h bar omega and omega can be defined as E by h k. Okay. H bar k is your what? Momentum p, and E is your p square by 2m, which gives you a value of what? P by 2m. This is the velocity of the wave. Okay. By that time, when this was evolving as physics, we already knew what? Momentum equal to mass into velocity. So now it is coming out to be P by 2m. P by 2m. We know the particles velocity is P by m. So what we found out is that velocity of wave is equal to velocity of particle divided by 2. That means that the speed at which the wave is traveling, it is half of the speed of the particle. Now that's a problem. This is a problem. First problem is that it is coming out to be constant. Now why it is a problem, I'll tell you. Now it is a problem, it is a very big problem. The particle is moving at speed very faster than the wave. So how can we associate that wave with the particle? We cannot. Now in this entire system, let's discuss first. Then this is complete. I'll discuss this part. This is a very important aspect of this study. Now look, why it is coming out to be constant? This is coming out to be constant because there is a violation of uncertainty principle already we are witnessing here. What is that problem? Here look, here the eigenvalue of the momentum is coming out to be exactly h bar k or minus h bar k. It is coming out to be exact. And if I tell you here, if I have to write the energy of it, it will be h bar square k square by 2m. Okay. This is the energy which is coming out to be exact value. The momentum is coming out to be exact value. In this situation, when both momentum and energy are coming out to be your exact value, won't we have delta E tends to 0 and delta P tends to 0? Then after this, we know that Heisenberg uncertainty relation is that, delta E into delta T has to be greater than or equal to h bar by 2, and similarly delta X into delta Px has to be greater than h bar by 2. Now if they coming out to be 0, delta T will tend to infinity and delta X will tend to infinity. Can this be possible in a state of our study? It is not. It is not. So we have found an equation, but we are seeing this equation doesn't sustain our data which we need. Now another big problem that comes to us is that this is your psi. In the first video we discussed that when we are calculating the wave function, we need a normalization constant. So we normalize the wave. In quantum mechanics, the wave function has to be normalized in nature. It can be square integrable. So it means when you normalize it, normalization means psi star into psi into dx. You have to integrate from the limits. Now in this system, there is no limit. It means we have to do it from minus infinity to plus infinity. So when you do that here, minus infinity to plus infinity, you can see here, it will be, this is the probability density, you will put probability density here, this is a constant, so constant will come out of the integration. Now you have to integrate dx from minus infinity to plus infinity, which will give you infinity. So this goes to infinity. This is another violation. So it tells you that this equation, this wave function, it cannot be represented that way. Now how will we represent it? Okay, now let's do that. Okay, I have to wipe it out again. Wave function which we used, it was a plane wave function. Now here, due to this inadequacies, we have figured out that the plane wave solution is not possible for a free particle. Now then, what kind of solution is possible? Then comes a very important fact of quantum mechanics, is that we define what is a wave packet. Now when we define a wave packet, it is a long calculation. You have to find, at the end of it, you will find a Gaussian wave function, you will find a Gaussian wave packet, the nature of that function, it will be like this, the peak will be like this, and it's a long derivation. But what is the form of that? Now this is what your wave packet is. Now this is how we define a wave packet. Now the derivation of this is very long. I'm not doing it. This is how we define your wave packet. Now you can do it very easily. You can also transform it like this. You can say psi of x0 can be done by this formula, 1 by 2 pi minus infinity to plus infinity psi k e to the power I k x dk. Now look at this. This is your wave function. What is this? This is nothing but your amplitude of your wave. Now how do we calculate this? This is calculated by using Fourier transformation, and Fourier transformation is one of the most fundamental chapters of physics. Here we define it as psi k is defined as 1 by root over of 2 pi minus infinity to plus infinity psi of x means x0, x means time is 0, e to the power minus I k x dx. Here it was dk, here it will be dx. Now what we do here is that this is how we transform a wave function. Look, this is a function where psi is defined as x. This is a function where phi is defined as k. This is the Fourier transform of one function into another. Now look at this formula. This is the formula of your wave of a free particle. If the question is about free particle, you remember this formula, that this is your wave function is defined. The wave function is not defined as a plane wave when we are dealing with a free particle. What we do there? We create a wave packet, and this is your equation for a wave packet. Now I hope you understand what I taught you. No, I didn't teach it. I explained it only. And I hope you liked it, and I hope it helped something maybe. If you want some improvements, you can tell me. And I hope you enjoy these videos if I keep making it. I don't know whether I will keep making it or not. That's a question. That's a very big question. Very big question.